Hey Chem fan, we've been learning about phase changes and how something as simple as water can go from solid, liquid, and gas. And notice a couple things again to point out. During a phase change, when an object is going through, like melting ice going from solid to liquid, notice that the energy doesn't change, it stays constant. Also with boiling water, when you're going from a liquid to a gas, the energy stays constant. That's super important because it shows that we aren't looking for a change in temperature. We're just looking for how much energy it takes to put into that system. So keep that in mind. Now remember, when ice melts, it starts to melt at 0 degrees Celsius. So this is 0 degrees Celsius the whole time here. Don't worry about that, I wrote that wrong. And then at 100 degrees Celsius, water starts boiling, all right? So over here is negative degrees Celsius and heating up to 0. It stays at 0 degrees Celsius when it's melting. When it's warming up to eventually boil, it goes to 100 degrees. And then when it boils, it stays at 100 degrees constant. So those are super important to realize and understand when we're doing these problems. But let's jump into it and see what we can do here. So how much heat energy is needed to warm? We've got 30 grams of ice. So we've got the mass of ice already, 30 grams. And it's at negative 20 degrees Celsius. So that means that it's below freezing and it's going to heat up and stay at ice to 0 degrees. So that means its initial starting temperature is negative 20 degrees Celsius, and its final temperature is going to be 0 degrees Celsius. Now, since this is at a negative temperature to start, and it's only going up to 0, that means that when we're looking at our energy chart here, we are simply staying in the A section, right, of warming up ice. We aren't melting it all, so we're not dealing with eventually going up and warming up to water. So we're just dealing with the A section. And if you look at the A section, it just says that our energy, which is Q, is going to be equal to our mass of ice, right there, times the specific heat of ice, okay, times the change in temperature, which is final minus initial. All right? Now, all we need to do is plug in to figure out how much energy or heat. So we're solving for Q. We have the M value right here. That's 30. The C value that we're looking for right here is just the specific heat of ice. Since water is solid right now, its specific heat is different than liquid water. So we are going to put that as 2.03. Again, because that's the specific heat of ice, and it tells you in section A. Since you're in section A, you use the A equation, all right? And then our final temperature was 0 degrees Celsius minus our starting temperature, which was a negative 20. Now be careful, minus a minus is really adding, so keep that in mind when you do your math. So here we go. If we start doing our math to solve for this to get Q, or the heat, minus and a minus mean a plus, so 0 plus 20 is really 20. So we'll make that 20, make that 2.03, make that 30, and then we're going to put that into our calculator. When we plug 30 times 2.03 times 20, we end up with 1,218 joules. Okay, and that's positive. What does that mean? Well, first of all, it took about 1,200 joules to heat up this ice cube to get it to its melting point from negative 20 to 0 degrees. So that's how much energy it took to heat it up to get there. All right? The reason it's a positive is because you are putting heat into the system, which means that that is an endothermic process because we are putting heat into the system. All right? So the numbers also correspond and correlate with the concepts we've been learning as well. But since this only was in one energy section and it didn't end up heating up or melting and it was still ice, we didn't have to go into this section. But occasionally you might overlap and have to do A, B, C maybe, and add up all of them. But in this case, we only were in section A, so that's all we stuck with. It was just one equation, all right? So it's important when looking at these problems, you look at where you're starting, where you're ending, and how that overlaps with all of these guys. You might end up in more than one box and have to add up and do numerous problems. Keep that in mind, but hopefully this is starting to get a little bit more straightforward for you. Keep up the good work, and let's go to the next problem. Looking at question number 2, how much energy is needed to warm 100 grams of water, remember water is liquid, okay, at 0 degrees Celsius, to still 100 grams of water at 100 degrees Celsius. So we're going from liquid to liquid here, which means there's no phase change. So we're straight up just warming up water. Looks like we're starting at 0 degrees Celsius and we're going up to 100 degrees Celsius. Now, why did I know that? First of all, this box says warming the water, and we know that we go from solid to liquid when we're melting, and we go from liquid to gas. So that must mean that this must be liquid and this must be solid. So since we're dealing with liquid water, we must be in this section, part C. So part C means we're dealing with this one, which is energy is equal to the mass of the ice times the specific heat. Forgive me, ooh, that shouldn't say mass of ice, by the way. That's a typo. That should say mass of water times the specific heat times the change in temperature. All right, so let's start plugging in. If we want to know how much energy, we're going to solve for Q. The mass is 100 grams. My specific heat, in this case, since it's liquid water, for water, is going to be 4.184 joules per gram degree Celsius. And my change in temperature, as always, don't forget, is the final temperature minus the initial. So my final temperature, I would end up at 100 degrees, and I would start at 0, so I'll subtract 0 from there. All right, so that ends up being 100 times 4.184 times 100. And when I rock that out, I'm going to add basically 4 zeros, remove the decimal point 4 places. 100 times all of that equals 41,840 joules. So what does that answer mean? First of all, it's positive, which means it's endothermic. You're putting energy into the system, and that makes sense because you're heating up the water. The water started around 0 degrees Celsius and heated up to 100 degrees. So it makes sense that you would be putting heat into the system. Putting heat into the system means that's an endothermic process. Perfect. Hopefully you saw some of the overlap with what we've already been learning with this phase change diagram. Question number 3 says, how much energy is needed to completely boil away? Okay, so boil away, that's an important phrase. Let's make sure we pay attention to that because boiling water is part of section D. But let's see where we are with our temperatures in that. So we've got 35 grams of water. It's boiling away at 100 degrees Celsius, and it becomes steam, 35 grams of steam, all right, at 100 degrees Celsius. Notice the temperature didn't change. So we're at 100 degrees Celsius and staying at 100 degrees Celsius. The only thing that could be is this section D right here, which is a phase change. You're going from liquid to gas, or as it said, you're going from water to steam. All right, so that must mean we're using, section D, which is energy, right here, is equal to the heat of vaporization, right, HVAP, times the mass of water. All right, well, let's plug in and get that. What is my heat of vaporization? Where does that come from? Oh, it's right over here. The product tells me exactly what to plug in. So I've got 22,060, and I'm going to times it by the mass. The mass stays at 35 grams the whole time, which it should. So I just multiply by 35. And what do I end up getting? Times it by 35, 79,100 joules. That's a 9. Sorry about that. 79,100 joules is the answer. Notice it's positive. That's because we are putting heat into the system. Again, notice during the phase change of going from liquid to gas, there was no change in temperature. That should be the case when you are going through a phase change. Phase changes stay constant in temperature. Just like if you were melting the ice. Notice the temperature doesn't change as well. It stays the same. All right, so that was good. We figured out what section to use and what equation to use and plugged in and got our answer. All right, problem 4 is going to be a little bit more involved. If you look, we need to know the total energy that's going to be needed to take solid ice is a solid, at negative 10 degrees Celsius and turn it to steam, which we know is a gas. Now, when something is frozen, it's a solid. When something is heating up like that, it's going to be a liquid, right? And then we're going to go from liquid to gas at this step. So we've got melting over here. We've got boiling at the end in section D. And now remember, water starts melting at 0 degrees Celsius, and it starts boiling at 100 degrees Celsius. So if this ice starts at negative 10, that must be somewhere in box A. And when it ends up at 100 degrees as steam, it must be somewhere in box D. So what does that mean? It means that all 4 steps are going to be included in order to find the total energy. So in order to find the total energy, right, and energy, remember, is Q, so the total Q, it's going to have to be equal to A plus B plus C plus D. In other words, all of the columns put together. All right, so let's do it. We got to start one at a time here. So section A, we're in this area right here. We are going to use this equation, Q equals MC delta T. Why? Because the chart says so. We are changing our temperature and we're looking for total energy, so we need to use Q equals MC delta T. Now, the mass that I'm using for my ice is 45 grams, right? Since I'm dealing with ice, I need the specific heat specifically of ice, which is 2.03. And I have to look at the change in temp. Now remember, in box A here, you started at negative 10 and you go up to 0 degrees Celsius. Because once you hit 0 degrees, you're going to end up in a new box, like box B. So that means your final temperature in this phase is 0, and your starting temperature was negative 10. So you take 0 minus a negative 10, which remember, 2 negatives make a positive. That's really like positive 10. So when I multiply all those 3 numbers out, 45 times 2.03 times 10, you end up with 913.5 joules. All right? So that's my energy for part A. Let's do part B really quick here. Part B is the melting phase, where you are going to use your heat of fusion and mass of ice. So in this case, the energy is going to be equal to the energy it takes to melt it, which is the heat of fusion, times mass of ice. And we can plug that in really quick. The heat of fusion is given to us up here. It's 334. And the mass is going to be the same. It's 45 grams. And when I multiply that out, 334 times 45, end up getting 15,030 joules of energy. All right, perfect. I've got A and B. I just need to keep going to get C and D. All right, part C. Let's take a look. Part C is warming up the water, which means you're going to be going from 0 degrees Celsius to 100 degrees Celsius. That'll be important because we need to know the change in temperature. Because in C, since there is a change in temperature, we're going to use our regular heat equation of Q equals MC delta T, which is final temperature minus initial temperature. All right? Plug in and chug out, and we should be good. We know it's 45 grams is the mass of the water. Now, we are going to take the specific heat of water because this is liquid water now that it's between 0 and 100 degrees. So we're going to use 4.184. That's given to us right here on the chart. That's specific heat of water. And then let's look at our change in temperature. You started at 0 in block C and you ended at 100. So that means you're going to end at 100 minus the starting of 0, which 100 minus 0 is just 100 degree change. All right, now that I have that, I'm going to multiply 45 times 4.184 times 100. And what I end up getting in my calculator is about 18,828 joules. So that means I had to put in about 18,000 joules to heat that water up from 0 to 100 degrees Celsius. And now that I'm at 100 degrees Celsius, I'm in my boiling water phase. which we know is all about the heat of vaporization. So to find the last amount of energy, I need to use the heat of vaporization for water, that's the energy it takes to boil, times the mass. And I know the heat of vaporization, it's given right here. It's 2260 joules per every gram of water, and times the mass, which is 45 grams. And the total, 2260 times 45, ends up being about 101,700 joules. All right, now that I've been through all parts of the phase change, I've got 4 heats here, or energy amounts, A, B, C, and D. I'm going to add all 4 of those up now, and what I end up getting for my total amount of energy is really 136,471.5 joules. Wow. How did I do that again? I added up this plus B plus C plus D. And why did I do that? Because this water sample started at -10, heated up so that it was still ice. The ice melted, became liquid. That liquid heated up, and then the liquid boiled all the way off. And that's the 2 major phase changes, melting and boiling, right? And we had to calculate the amount of energy it took to do all of those individually in 4 separate sections, A, B, C, and D. And that, of course, led to us adding up all of them, A, B, C, and D, to give us our total energy. All right? I hope that helped, ChemFam. I think that's a great way to get started and some guidance on these problems. But as you can see, we're using an equation we've already learned about, Q equals MC delta T. And we're just using another short equation because we've introduced the heat of vaporization and the heat of fusion at this time. All right, good luck. Keep working hard.